Hi, this is the third video in chapter 3. By the way, I changed my video capture on to the top right from the bottom right because I realized that the page number is not shown on the video. Just in case if you wanted to refer to the slides, then it would be uncomfortable if I block that. My face, my useless face blocks the page number, so I relocated my face to here. Anyhow, it does not matter. Here I'm like in the previous video I defined the what is the average, and also so based on the definition I showed you how to calculate the unified way to calculate the average. It depends on the format of the data, either raw data or frequency or probability distribution table. So in both cases, if you understand the definition, then it'll be natural, like it is easy to calculate the average. Now I'm going to start another example, which later on becomes more complicated. So imagine that you own a car dealership, and you would like to evaluate a car salesperson's sales performance, right? Salesperson's performance is measured by literally sales. So you looked at her past sales record, like weekly reports, reports on how many cars she sold in each week, and from the past 50 weeks observations, you found that 25 weeks could not sell any car, but in 20 of the past 50 weeks, she sold one car per week, and 4 weeks she could sell two cars, and in one very lucky and a week she sold three cars a week, right? So this is a frequency distribution table. So we are going to start from here to calculate the average. First step is to transform the frequency. We observe 50 different weeks, and we count how many weeks this salesperson sold specific number of cars in a week. And what is the probability that this person sells three cars a week? More generally, you can make another column to calculate the probability distribution table. I believe it is simple. Okay, so I'll turn the page. If you want more time to do the algebra, pause the video. So this is the probability distribution table, right? So by the way, the probability underlying experiment is randomly choosing a week from the past 50 weeks. It's like time series data. So a 1 week is one experiment, right? So and each week the outcome is how many cars you sell. So if you randomly choose a week, then you observe the number of cars sold. And out of 50, you observe only 1 week in which she sold three cars. So that is 1 out of 50, 2%. Now you are ready to calculate the mean because you have outcome and you have the probability. So now calculate the mean weekly sales. Right? It is probability weighted outcome. So you have everything you need to calculate that. So again, pause the video and try it by yourself first. Basically, it is to make another column here by multiplying probability to the outcome, and then sum whole column to get the mean. Okay. Okay, I'll show you the answer. This is what I meant. You have to calculate probability weighted outcomes by multiplying outcome to probability. That one, like 0 times 0.5. It is interesting that because the outcome is 0, no matter how likely it is, weighted outcome is in the end 0, right? So that is natural. And like multiply line by line, then you get 4 probability weighted outcomes. 0, 0.4, 0.16, 0.06. So that are 4 different numbers, and summation is 0.62. That is the average sales for this salesperson. This salesperson sells 0.62 cars a week on average, right? This is a summary of the salesperson's performance. Okay, so easy to understand. From now on, I am going to think about more extended scenario, like additional assumptions. Suppose that if she sells a car, then you are the owner of the dealership. So if she sells the car, then you get a profit of $3,000. Suppose right? So that is the markup. Like when you sell a car, uh, you get $3,000 from selling a car, but you have to pay the salesperson. But salesperson's salary is weekly. It does not depend on the actual sales, right? We assume that there is no incentive, and the salesperson is simply paid a weekly salary of $2,000, right? Of course, these numbers are made up to simplify the algebra. So the I don't know how much the profit and the sales salary are in an actual dealership, but suppose they are 3,000 and 2,000. Then I would like to evaluate, I'd like to evaluate if the salesperson deserves raise or uh, like should do better, right? So the average sales 0.62 is a nice summary, but hard to interpret if this salesperson is good or bad, right? To make a decision, better decision, more informed decision, we have to take these into account and recalculate the expected net profit, right? So of course, what you need to do is you have to calculate the profit from selling a car minus the salary you are paying to the salesperson. That is your actually net profit. So we are calculating the expected net profit. Okay. How can we do that? It's not that difficult. Just you can convert the weekly sales, the number of cars, into dollar, right? Using the assumptions. For example, if no car was sold, then simply you are paying $2,000 to the salesperson for nothing, right? So your net profit is minus 2,000. But if the salesperson sells one car a week, then your net profit is $1,000. The salesperson made 3,000, but take 2,000, so 1,000 is the net profit. And as the salesperson sells more cars, your net profit increases, right? So two car means when she sells two cars, then your net profit is 4,000 because she generated 6,000, but the salary is only 2,000. If she sells three cars, she generated 9,000 but takes only 2,000, so 7,000 is net profit to you, the owner. Okay, so it is simple transformation, but like statistically, what you have to observe here is basically event-wise, these are the same thing. Just I'm referring to the same event of selling zero car, but I put different numbers. So you may put zero because zero cars are sold, or I may put minus 2,000 as an outcome because this is your net profit. So for the same event, there are different ways to number that, to label the same event with different numbers. You may use number of cars or dollar amount you get. Okay, so uh, that means even though the numerical outcome can be different, but the probabilities are the same. Probabilities are attached to the event, not the number, right? So as long as the underlying events are the same, no matter how they are called, no matter how they are numbered, the probabilities must be the same, okay? So that means the probability distribution for number of cars must remain the same for the probability for the net profit, like this, right? So I just change it 0, 1, 2, 3 into minus 2,000, 1,000, 4,000, 7,000 because I just changed it the unit from number of cars to dollar. But this part does not change because the events are the same, because the probability is a function of the event, and the event, as long as the events are the same, probability does not change. Now, then, based on the same probability, you can calculate the expected weekly net profit. Try that. So again, pause the video and do it by yourself, right? If you have no idea, just go back to the previous question and then follow the same steps. Basically, it's the same structure. You may use a calculator or Excel if you want. So let me turn the page. So the idea is to multiply line by line and sum and make another column and sum out the column like this, right? So multiply, 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 and multiply, right? And sum these numbers, you get minus 140, right? That means this salesperson actually incurs a net loss of $140 each week on average to you, right? Some case in some weeks, she's making positive profit, but 50% she's making minus 2,000, right? So then it's hard to tell without calculating the average, hard to tell how she's doing. But when you calculate the average, it nicely summarizes one number to evaluate her performance. Basically, she does not deserve the salary. You may fire her or you may lower her salary. That's justified by this average, and as I said, the average helps you make an easier decision, easier comparison, easier evaluation. Okay, so that's the story of this example. But we will try to extract some like new mathematical properties from this observation. So remember this number, minus 140. We will think about more general case, right? Basically, what you have done is a transformation of random variables. As I said, it is changing unit. Like it is just labeling the number different ways. For example, euros and dollars exchange rate is just say the same value. Like for example, like the computer is say like $500 in the United States, but it could be I don't know how much it is, like 600 euros in Europe, right? So then the value is the same, the same computer, but the units are different. Similarly, inches to meters, same length, but you put different numbers depending on the unit, like Fahrenheit to Celsius. Like in our example, number of cars or the net profit. Basically, they are the same thing, but measured in different units, right? It is a transformation of the number, right? So in more general, you can think it like this. X, random variable X is a original random variable you have data about or you observed its probability. But you are interested in Y, like different units. Like we saw, what you are interested in is net profit, not the number of cars itself, right? So X is original random variable, then you have to transform X into Y. So mathematically, you can think about another function. If you enter X, then this function gives you Y. Y is the variable of your interest. So in our example, it looks like this, right? The net profit you get is 3,000 times X. So for each car you sell, it generates $3,000. So 3,000 times X, but minus 2,000. 2,000 is the fixed cost to the owner because you have to pay the salary no matter how many cars she sells, right? So this is the transformation from the original variable, number of cars, into a new random variable, y. Okay? So, what we just did is calculating the mean of y. So in our example, we have information about x, and we have information about the relationship between y and x. Based on these two types of information, we are interested in the mean of y. How do we do that? Transform x into y using the relationship and assign the probability to each y, right? I said the transformation is just like renaming the same event using different numbers. So probability basically does not change. The main point is you have to tell which events are the same. Like same event has the same probability after renumbering. And then finally, then you can calculate the mean from the probability of y. So this is what we have done. But then a natural mathematical question is like this. Okay, if we know expectation of x first, like we already calculated that the salesperson sells 0.62 cars per week. That is on average of x, right? This we already calculated the average of x. Is it possible to utilize this information to calculate the average profit? The answer is no. In general, unfortunately, no. But in some special cases, yes, it helps. So, like in our example, so we already calculated that the salesperson sells 0.62 cars per week. And we get the relationship like this. And then you may just replace x with the expected value of x in this relationship. So this is the relationship between y and x, but replace the y and x with their expectations, right? So expected value of y is 3,000 times expectation of x, which is 0.62, minus 2,000. Just follow the relationship and plug in the expected value of x. Then you get 140 minus 140. Exactly the same result we get from the full steps, right? But remember, this is true only in a very special case. That is when the relationship is linear, right? You must have heard about a linear function, linear mapping, right? So this is linear function. Y is a linear function of x. In general, a linear relationship takes this form. You get y only by multiplying something and adding something. Of course, it could be like division, like if you put 1 over a. So like dividing by a means multiplying 1 over a. So it includes like division. And also subtraction is included if b is minus, right? So if b is negative number, that means just subtracting some number. So anyhow, linear relationship takes this form. Then if the relationship is linear, you have the same linear relationship for their expectations. So it could be easier to utilize this property. But as I said, the point here is the result is simple. But what the additional cost, you may use the easier result at the cost of verifying the relationship, right? So it is important to see what is linear and what is not. Examples of nonlinear relationship is like this. Quadratic function, like x squared, right? So when you multiply x to x, that is not linear at all. You can only multiply a constant, not x itself, or any other random variable. This is not linear, and this is not linear. So there is a cutoff. If x is greater than 0, y is 1, but if x is smaller than 0, y is 0. Like it is, like it's there is a discontinuity when x equals 0. So this is not linear. And not like one famous example in economics is the utility function. Utility function is not linear usually. It is concave, like it goes like this. Increase is steep, like for the first, like when x is small, but it becomes more flat, right? So steep and then flat. It is concave function. It is not linear, right? So this is what complicates the expected utility theory. If the utility function was linear, it's so simple. But because it is not linear, you get a whole new theory, interesting theory, and how people handle risk when things are random. So that's a new economic theory. So related to that. Okay, so in the next video, I'm going to give you a new example to study what is linear, what is not, and how they differ in general. Okay, see you in the next one. Bye.